Hey everyone, and welcome to this tutorial for a NACA2412 Airfoil in ANSYS Fluent. We're going to go through the full steps of creating the geometry, the mesh, and setting up the simulation in ANSYS Fluent. I'm going to do this simulation in ANSYS Student so that anyone watching this video can conduct the simulation at home by simply downloading ANSYS Student and conducting the simulation, or by doing it on the full version also. In this tutorial, we're going to calculate the drag coefficient, the lift coefficient on the airfoil. We're going to also plot the velocity contours, the pressure contours, and the velocity vectors of the flow field. We'll also then change the angle of attack and show how that affects how we model the simulation in ANSYS Fluent, and we'll also show how varying the angle of attack will change the flow field surrounding the airfoil. So go ahead and load up ANSYS on your computer and let's get started with this tutorial. So the first thing we want to do here is drag an ANSYS Fluent analysis system into the project schematic, like so. Now the first step is geometry, so we need to go ahead and get the NACA2412 airfoil curve and import that into Design Modeler. So how we do that is simply to look up on Google airfoil plotter NACA2412. So here's our airfoil. We'll leave all these digits the same. This basically is identifying that this is the NACA2412 curve shape that we want. And number of points here, we're going to change this to 200 because we get the choice between 200 and 20 points. So we're obviously going to pick 200 as it's going to be just that little bit more accurate. And also we're going to close the trailing edge here because we don't want a hole at the trailing edge here in our curve, as we're going to get errors in our simulation then. I'm going to go ahead and click plot here and send to airfoil plotter. And one last change I'm going to make here is to change the chord to be 1000 millimeters, which is 1 meter, as this is the standard size for airfoils, and it'll make calculating the Reynolds number and velocity just a little bit easier. So once that's done, I'm going to click plot again, and my airfoil is ready to go, and I'm going to click CSV file of coordinates. So this will give us an Excel file that will edit a small bit before we can import into Design Modeler. So I'll download that file and then open it. Okay, now once I've downloaded this file, there's a few edits we need to make to the file so we can actually import this into Design Modeler. So the first thing I'm going to do is get rid of all this stuff at the top here, as there's no need for it. So I'm going to click this top row, hold Control, and come all the way down. Sorry, hold Shift, all the way down to this row, and I just want to delete all them rows there. I'm going to insert 2 rows here, 1 and 2 on the left. I'm going to change this very left column here to be hashtag group. I'll explain this shortly. This next column to be hashtag points, hashtag X, hashtag Y, and hashtag Z. So hashtag group, this is essentially I believe it's the type of point. All I know is that we're going to put in here the 0.1 for all of the coordinates here, and that seems to work when we implement it into ANSYS. So that's what we put in here for group number, and then for point number, we're going to put in 1, 2, 3, 4, and all the way down until 200. So how I do that, how I speed up this process here, is to do equals, click the row above, and then click +1, and then I'm going to drag this formula here. So this little green square here, I'm going to drag that down all the way down to my 201st point, all the way down to here. I'll remove this in a minute, we don't need that camber line. And lastly then the Z coordinate. Even though we are doing a 2D simulation, we'll just put in here Z equals 0, as ANSYS expects it in the file that we're going to upload. So put in 0 here, drag that down all the way to the end. Now we don't need any of this stuff here, camber line, and I think there's some more stuff at the bottom, camber line and chord line. We don't need that, delete that. And one last change you want to do here, so you can see at the end here, basically the points start to repeat itself and it goes back to 1000, which is the same as the top coordinate, because it's trying to basically indicate that it wants to close the trailing edge. But how we actually do that in ANSYS Design Modeler is we remove this point here, like so, and change this to 1, 0, and then that will close the trailing edge of the airfoil, so we have a fully closed curve. And that's everything we need to do here to upload this file into Design Modeler. So I'm going to save this in my downloads as a very bad practice, but nonetheless, just for video purposes. So I'm going to call it NACA2412, and I'm just going to call it a video because I have this file done before. And this needs to be a text file in tab delimited format, just like so. And hit save. Yes, that's okay. And our file is now ready to go to be imported into Design Modeler. Alright, now that we've created the airfoil curve in Excel to import into Design Modeler, we're ready to go ahead and create the full geometry. So to do that, I'm going to right click on Geometry, hit Properties. I'm just going to change the analysis type to 2D, as we're just going to do the 2D airfoil today. Then right click Geometry and load up Design Modeler. Once Design Modeler is opened up, I'm going to look directly at the XY plane and go to Concept, 3D Curve, and here we're going to import the curve we just created in Excel. So I first need to change my coordinates to millimeters, as that's what we had our coordinate file in. I'm going to go to Downloads and I'm going to click the file that we created. I'm going to import that and hit Generate. And now the airfoil file is created here. So I'm just going to click on Zoom to Fit just to take a proper look at it, and all looks okay here. So now what we want to do is we want to create a surface from this curve, and then later on what we'll do is we'll remove the airfoil surface from our fluid domain. So to do that, what I need to do is go to Concept, go to Surfaces from Edges, click the curve, hit Apply and hit Generate. And what you'll see now is we now have a surface representing our airfoil. Okay, so now I'm ready to go ahead and start making the fluid domain around the airfoil. And for this case, I'm going to do a C-shaped domain. You can do an O-shaped domain too, where you just make the domain of fluid a circle around it, but I'm going to make a C-shaped domain as it converges a little bit better. So a C-shaped domain is going to have a C in front of the leading edge and then a square behind the leading edge. So to create that domain, I'm going to go to Sketching, Create. I'm going to create a semicircle then in front of the leading edge. So Arc by Center. I'm going to click here at the origin, but I want to click when I see this P here, as that's letting me know that I'm directly locked onto the origin, whereas the C just lets me know that I'm coincident to the x-axis. So once I see the P, I click, and now I want to create the arc of the circle to be in line with the y-axis. So I click once I see this C here, and the same again down here. Click once I see the C to let me know that I'm fully in line with my axis. Okay, let's add some dimensions here. So I'm going to make this domain about 15 chords surrounding the airfoil, as I found from previous studies that this is sufficient to give accurate results. So I'd like it to be 15 chords from here till here, from one end of the semicircle to the other. So that means the radius of this circle would be 7.5 chords, which would be 7.5 meters, because you remember we made the airfoil to be 1 meter in chord length. So I'm going to make this 7.5 meters as the radius of the circle. Now I'm going to create the rest of the domain, which is just the square part behind it. So I'm going to click here once I see the P to be locked onto that point, create a horizontal line indicated by that H, and dimension this line to be 15 meters, which is 15 chords rearward of the leading edge. Now I'm just going to fully close the domain. And it's important here that I click once I see this C here, just so I don't have to add in an extra dimension. And that's my domain fully closed. Now there are a few more sketches that I'm going to add in here to the domain, and that'll help me with my meshing later on. So there are 2 extra lines that I'm going to add in here, and this will, you'll see later on, I can add sizings to these lines later on in the meshing software, and it makes the meshing far more structured and far easier to define. So I'd like a vertical line here at the trailing edge of the airfoil, not the leading edge. So I'm going to create a line just like this, and it's not exactly at the trailing edge right now, so I'm going to dimension this to be 1 meter from, I'm just going to delete that, that's a vertical dimension. I'm going to create this to be 1 meter from the origin, just like this. And once that line is created, I'm going to extend it to the end of the domains by clicking Modify, Extend, and just that'll extend it to the end of the fluid domain. And now I want a vertical line near the leading edge of the airfoil, but not exactly. So I've found that if I create a vertical line that's about 80 millimeters, in the case for this airfoil, for the NACA2412 airfoil, this is the case that I found. If you're using a different airfoil, it may be different, but for this particular case, I've found to create a vertical line at about 80 millimeters from the origin here gives pretty good results in terms of a nice mesh. So this line here, I'm going to do 0.08 meters, which is 80 millimeters from the origin here, and then I'm just going to do the same, extend this to the end of the domain. Okay, and they're the lines that I need now to properly define my mesh in a nice structured way. So once I've created my sketch here, I'm going to turn this into actual lines. So to do that, I'm going to go to Concept, Lines from Sketches, and just select the sketch we just created. Hit Apply and then click Generate, and you'll see we have actual lines now that we can do some more interesting things with. Once we have lines, we can turn this into a surface. So to do that now, I can go to Concept and go to Surfaces from Edges and select all the outer edges of my domain. So be careful of this very small line here, and while holding Control, I select all the outer edges of the domain and then hit Apply. And you'll see we get a surface here that we're going to use to represent our fluid surface. But if you notice, if you look in the tree, that ANSYS has created a solid surface and we want a fluid surface. This is going to represent our full fluid domain. So I'm going to switch this here to fluid and then hit Generate. Okay. Now that I have a fluid surface, what I want to do is I want to remove the airfoil surface we created at the beginning from the fluid domain. So we have an airfoil shaped hole in our fluid domain, which will represent the solid airfoil. So to do that, I go to Create, Boolean. I'm going to do Boolean subtract. The target body is the fluid surface and the tool body is going to be the airfoil surface. Now to select the airfoil surface, what we need to do is click the airfoil here, but you'll see ANSYS actually selects the fluid surface we just created. We don't want that. We want to select the airfoil in behind that. So we need to click this plane here and you'll see it highlights the airfoil surface. Then I hit Apply and then click Generate. And you'll see we're now left with a fluid surface here with an airfoil shaped hole in the domain, and this hole is representing our solid airfoil, of course. Now there's one more thing I need to do before I can bring this to the meshing software, and what I need to do is I need to split the domain into different faces from the sketches that we created to help refine our mesh. So to do that, I'm going to go to Tools, Face Split, select this face here, and we're going to split the face by the sketches that we created. So select the lines that we created earlier on, these lines here, and we're also going to select the x-axis here so that we have 6 total faces. Hit Generate. We have 6 total faces now in our domain that we can mesh separately. Now there also is one more thing I need to do, and I was getting errors with this small edge here, so I'm just going to combine it with this larger edge here as it makes it far more easier to mesh. So to repair this edge, what I'm going to do is I'm going to use the edge selection filter, hold Control, click this edge here and this edge here, go to Tools, Merge, and you'll see we have merge type as edges, and then hit Apply and click Generate. And what you'll see is now, instead of having that small line and the larger line here, this is all just the one line now, all the way up to this point here. And we're going to do the same thing for this lower half of the domain. I'm going to click on this edge here, hold down Control, and then click this edge here, Tools, Merge, and Apply, and click Generate. And just to check that that's merged the 2 lines together, when I click this line here, this is my full edge now, which is exactly what I wanted. So I'm ready to go here to bring this to ANSYS meshing. So now it's time to properly save the file. So properly saving files in ANSYS is really important. If I go to File, Save As, and save my project somewhere, I really don't want to just save this to my desktop or my downloads folder or even into my documents folder, because what's going to happen is ANSYS is going to save some extra files alongside this file, and if we just save it into a folder, all these files might get lost, the files that we need to actually open our project. So what we need to do is to create a working directory, or in other words, just create a folder specifically for this project. So what I'm going to do is I'm going to go to Documents, create a new folder here. I'm going to call this NACA2412 Video, and then inside that folder I'm going to create the project file, and I'm just going to call that the same thing, NACA2412 Video. Now if I go to my documents and look at the folder I created here, you'll see that where I saved my project file, which is the file we're working off here, there's these extra files in here. So this is what I meant when I said that ANSYS is going to save some extra files, and we need these extra files in order to open our project. So this is why it's important to create a proper working directory and a designated folder for your project. Otherwise these files are just going to get either lost or they'll be dumped into a folder where you don't want them, for example on your desktop, in your downloads, in your documents folder. So we don't want that. So it's really important you create this folder for your project. Okay, so once that's done, we have our project saved and we're ready to move on to the meshing step. To start meshing, I'm just going to click Edit, and this will load up ANSYS Mechanical. Once ANSYS Mechanical is loaded up here, I'm just going to look at the XY plane again, and as you can see here we have a line body from the sketches we created. I'm just going to go ahead and suppress that body as we don't need it anymore, as we've split our domain into different faces, so there's no need for that. Now I'm going to add some edge sizings here to the mesh, and to do this I used there's another tutorial on YouTube from a guy named Anthony T, and I'm going to use the sizings that he used in his video, as he managed to get a very structured mesh with these particular edge sizings. And I'd recommend after this tutorial, if you're still struggling to model in Airfoil, to go and look at his tutorial because it's very good. So yeah, we're going to use them edge sizings in this mesh, and then we'll determine afterwards if the mesh is suitable to this airfoil. So I'm going to insert a sizing here, select these edges here while holding down the Control key, hit apply, change this to number of divisions, 250 divisions, and then I'm going to add a bias here, select the first option and create a bias factor of 50,000, and that's going to basically bias and give us more elements towards the airfoil than the outer edge of the domain. But you'll see here that some of the edges are actually flipped in the wrong direction, where we have bigger elements close to the airfoil and smaller at the edge of the domain. So we're going to go ahead and reverse all the edges that are in the wrong direction, and to do that we click on reverse bias, hold down Control and click all the edges that are in the wrong direction, and then hit apply. Now we're going to add some more edge sizings here. I'm going to select all three edges here, hit apply, do number of divisions, set this as 150, set the behavior to hard, and then create a bias again with a bias factor of 300. Now, and I'm going to reverse these two edges here also. Now you'll notice I set the behavior as hard here, and what this basically does is it inflicts on the software a very stringent condition that we want 150 divisions here, no more and no less. And that's what we do when we have a very simple shape that we're trying to mesh, such as this square. But as before, we used a soft meshing condition as we're meshing multiple different edges, and basically when we use the hard condition we get a very structured mesh. So we're meshing very simple structures. It's okay to use this hard condition and we get a very structured mesh. But when we're using the soft condition, we mightn't get as well a structured mesh, but we're less likely to run into errors with the meshing. So in any other CFD simulations that you might be doing, if you're meshing a very simple shape such as a square or a rectangle, we can often use the hard condition and get a very structured mesh. But if it's a structure that's not very simple, and then often using the soft condition for the element size behavior is often a better option, as then otherwise you'd run into errors using the hard condition. Nonetheless, let's continue on with our edge sizings here. So I'm going to select these 4 edges here, top and bottom of the airfoil and bottom of the domain, hit apply, number of divisions 150 here, and set the behavior as hard. And then lastly, we're going to select these 4 edges here, the outer edge, front of the airfoil, and the bottom of the domain. Hold Control and hit apply, and we're going to do 100 divisions here for these edges with behavior as hard also. Last thing we need to do is to add a face sizing here to let us, the software, know we want a quadrihedral mesh instead of triangular mesh. And to select all the faces, just press Ctrl A on your keyboard, hold Control and hit apply, and then click generate, and we'll take a look at the mesh. So once the mesh has loaded, we can inspect it a little bit, just have a look at how it looks. To be honest, it could be improved a bit more. If I were to do this again, I would probably reduce the length of this point here towards the leading edge of the airfoil, so less than the 80mm that I used, maybe to 40, as what's happening here is I'm getting kind of a squished mesh here, and the volume is going to change a lot from each cell, from this cell to the next one, which is not what we want. And these elements are also pretty skewed, which is fine because it's far away from the mesh, but yeah, there could be some improvements made to this mesh for sure. But for purposes of this study, I'm going to leave it alone for now, because I'm just going to go ahead and get a solution and show you how to run a simulation rather than focusing on getting the mesh perfect, because mesh generation itself really is an art. So the one last thing that's really important that we do need to check, besides from mesh quality, is to take a look at the Y plus value at the airfoil wall. So what the Y plus is it's a non-dimensional value that lets you know how much of your mesh is capturing the viscous sublayer. So in order to capture this non-linear behavior of the velocity profile at the wall, you need to have a Y plus of 1. And the reason for that, as you can see, is this is a Y plus value of 1 here. And then as we go along here, we get this non-linear behavior all the way. So in order to capture this non-linear behavior of the velocity at the wall, we need to ensure that our first cell height is at what's called a Y plus of 1. And we can use a calculator in order to figure out what our Y plus value should be. So in other words, how big should the cell at the wall be in order to capture this non-linear behavior of the velocity at the wall. And this is going to be important for this airfoil simulation, where we're concerned about maybe the adverse pressure gradient at the wall and looking at the separation length across the airfoil. So it's important to have a Y plus of less than 1 where wall effects are important, but for other simulations where wall effects are not important, it might not need to be captured. So nonetheless, for this simulation, we're going to aim for a Y plus of less than 1, and it will actually be an output of the simulation because it's a function of the velocity profile, and we don't know the velocity until we solve the final simulation. But nonetheless, we can use calculators to get an estimate of what our Y plus is before we start the simulation. We can then go ahead and calculate our solution, and then we can get the Y plus as an output to see if we've kept a Y plus of less than 1 in the majority of the mesh. So to calculate what value our cell height needs to be to get a Y plus of less than 1, of course we need to pick a Reynolds number of the flow. And the Reynolds number I'm picking for this case is compared to this experimental data from Abbott, and I will leave this also linked in the description so you can have a look at this experimental data and run some different simulations yourself. But here's a NACA2412 airfoil with the lift coefficient versus angle of attack, and the drag coefficient versus the lift coefficient. And there's a list of Reynolds number here, so I just picked an arbitrary Reynolds number of the first one here of 3.1 by 10 to the 6. And by using this Reynolds number in our simulation, we can then compare later on our lift and drag coefficients to this experimental data. But nonetheless, now that I know my Reynolds number for the flow, I can calculate what the velocity, the mainstream velocity of the flow is. So by rearranging the formula for the Reynolds number, this is wrong for the viscosity here. I actually use 1.802 e to the minus 5 because this is air at 288 Kelvin. And using these values, I got a mainstream velocity of 45.6 meters per second. Now, to calculate what value our first cell height needs to be to get a y plus of 1, I can input these values into a calculator. So I used 1.802 e minus 5 here for the viscosity. Our reference length is going to be our chord length, which was 1 meter, as you remember, and we want a y plus of 1. I need to put in the mainstream velocity here, 45.6, and it should be much smaller than this. So this is our value in meters, so I'm going to convert this to millimeters just so it's a little bit easier to see in ANSYS. So meters to millimeters. So we need to have 0.008 millimeters as our first cell height thickness. So when I go to ANSYS here, and let's take a look at the airfoil, we want to zoom into the wall and try and get an estimate of the first layer height. So zooming in right down to the boundary layer, what I can actually do is press this selection here to select a node. And if I select this node here and this node here, you can see that the distance from the wall of the first cell height is equal to 6.3 e to the minus 3 millimeters. And the wall height that we need to have a y plus of 1 is equal to 0.008, which is 8.2 e to the minus 3. So this value here is less than what we need for a y plus of 1. So we know that we have a y plus of less than 1 in the boundary layer, and we're going to capture all the boundary layer effects in our simulation. But of course, I think it really is important to state that the y plus is an output of the simulation. So actually, the y plus value that we just got is an estimate, and the y plus value that we need, the cell height that we need to maintain a y plus of 1 will actually change over the wall. So it is important that we check this after the simulation and ensure that a y plus has remained mainly below 1 all around the airfoil wall. One last thing we also need to do is we actually need to create our boundary conditions for Fluent. So what I'm going to do here is I'm going to zoom in on the airfoil, select the edges of the airfoil here, press N on my keyboard, or actually what I should do is right click and press create name selection, just in case you don't have that shortcut enabled. We're going to name this airfoil, and that's going to be our wall condition. And we're going to select these outer edges here, all outer edges, create a name selection, and we're just going to create this as our inlet. And then finally the edge here is going to be our outlet. And now we're almost ready to go. What we're going to do is we're going to press update, and what this is going to do is it's going to send the mesh to Fluent. And what that does is it gives us a green tick here on our mesh, letting us know that everything is done, it's fully saved, it's gone to Fluent. So file, close meshing, and I'm going to save the project one more time just before we go to the Fluent solver. Now I'm going to click on setup, right click and press edit, and we're going to start Fluent. I'm just going to enable double precision, and I'm going to use 4 cores here because I know I have 4 cores on my PC, and that's the limit on the student version as the maximum number of cores I can use. If you don't have more than 4 cores or 4 cores, that's fine. It's just going to affect how fast you solve your simulation. So once Fluent loads up here, we're ready to get going with our simulation. So once everything is loaded up, I'm going to go to General, and we're going to leave pressure based and steady for this simulation. Let's go to Models, and I have the SST-K Omega model selected for the airfoil. And this is a great model for predicting airfoil separation, especially when you have a y plus of less than 1. This is generally recommended for airfoil simulations, so I'm going to continue using this model for this simulation. So now I'm going to go to Material Properties here, just double click Materials, go to Fluid, and have a look at the properties that I have for air here. So the density is okay, but I believe I had a different viscosity. So I used 1.802 as my viscosity, so I'll change that here. And hit change create. So now let's click on boundary conditions, have a look at the inlet. We have a velocity inlet here, which is exactly what we want. And just for good practice, I'm going to change the velocity to be in components. And we want the x velocity here to be what velocity we had calculated for our Reynolds number, which was 45.6. So 45.6 for our x velocity, and hit apply. Let's have a look and make sure that the name selections we created are all okay. So the airfoil here is set as a wall condition, which is correct, and the outlet is a pressure outlet. And the gauge pressure here is 0, so that basically means that the pressure at the outlet is 0 pascals above atmospheric pressure. And how I know that is if I look at operating pressure, I'm operating at atmospheric pressure, and then the gauge pressure would be the value above our operating pressure, which is 0 here, which is exactly what I want. The outlet is essentially at atmospheric pressure, which is what I want. I'm going to leave all the settings alone here. I'm going to go to reference values, and I'm going to compute from the inlet. And this is important because we're going to be calculating drag and lift coefficients, and we need the values to be the same as the values we use at the inlet. Otherwise, our drag and lift coefficients will not be calculated correctly. Now I'm going to go to solution methods. I'm going to leave all the default settings here as second order upwind and using the coupled pressure velocity scheme. I'm going to go to residuals, and I'm going to reduce this down to 1e to the -6 because we're running a very simple kind of simulation here, so I'm perfectly fine with restricting a more strict convergence condition on the residuals here. So then we're going to go to initialization. Hybrid initialization is fine. You can use standard if you want. All this basically does is solving the finite volume method is an iterative solution. So we need to assign the cells an initial value or an initial guess so that the simulation can proceed to continue. So it doesn't really matter which initialization scheme we use, it just affects the path to convergence. So I'm just going to use hybrid here and initialize the solution. Okay, once it's initialized, we have a few more things we need to set up here. So I'm going to basically set up the drag and lift coefficients to be an output of the simulation so we can look at how they're converging. So to do that, I go to right click on report definitions, a new force report, and we'll do drag. We'll change this to drag coefficient. Keep it as drag coefficient, and we're looking for the drag coefficient on the airfoil. Force vector, leave that alone. We'll talk about that when we change the angle of attack. We want to print it to console and print a report file too, so that's all okay. So that's our drag coefficient done, and now we just need to create one for the lift as well. So we're going to new force report lift, click on airfoil, lift coefficient, and we want to print this to console too, and then click OK. Double click on run calculation, and let's just do 1000 iterations, and that should be plenty for the solution to converge. So that's everything we need to define, and we're ready to calculate the solution. So once I click on calculate, then I should get a graphic window showing me the lift and the drag coefficients and how they're converging with the number of iterations, and I should also be able to see the residuals and how they're converging. And as I said, this is a very simple simulation, so there should not be too many problems with convergence. It tends to be with unsteady simulations or simulations with heat transfer or something like that that we might have issues with convergence. So I'm not expecting any errors or any difficulty in convergence of this simulation. And you can see we have the lift and drag coefficients also being reported to the console, and we'll compare these final values to the experimental data from Abbott. So here's our drag coefficient, our residuals, and our lift coefficient. And how we'll know that the solution is converged is essentially when the values just are not changing too much from one point to the next. And you'll notice that the residuals will keep decreasing all the way down to the value that we've set them to usually, but the lift and the drag coefficient tend to converge a lot sooner. So for accurate lift and drag coefficients, we might only need a couple hundred iterations before the value of the lift and the drag don't change too much more. So you can see that the lift and drag coefficients have not been changing for a while. but the residuals are still going down, so I'm going to leave it for a while. You can see, yep, here's our drag coefficient here on the left, sorry, our lift coefficient on the left and our drag on the right. So I can go ahead and check this against the experimental data while this is running, just to see if we're on the right track. So if I go to the experimental data here for a 0 degree angle of attack, which is what we have in our test case, for a Reynolds number of 3.1 million, if I go up along this line here and have a look at the circular dot and zoom in, so 0 degree angle of attack, it's quite difficult to look at, and go across, it's somewhere in between 0.2 and 0.3 for sure, probably about 0.25 for the section lift coefficient, and what we have here is a lift coefficient of 0.218. So in terms of error to experimental data here, you're looking at about 0.218 divided by 0.25, which is about 13% error, which to be honest is quite good, especially considering the fact that we haven't done a mesh independent study, we haven't done a domain study, so we haven't varied the size of the domain to have a look at how that affects the results. And nonetheless, this is CFD, this is a steady simulation, there's lots of assumptions embedded in here, and to compare that to experimental data and get only a 13% error, I think is very, very good, especially for CFD. Now let's take a look at the drag coefficient. So we have something like 0.009, and if I look at the data on the right here, for a lift coefficient of 0.22 would be about here, and I scroll up, the circular dot here for the drag is at about, if I go across here, is at about, the line below is 0.5, 0.6, 0.65, 0.0065 for the drag coefficient, and you can see there's a little bit more error here on the drag coefficient. So if I go to calculator and do 0.0065 divided by 0.009, let's round that up to 7, yeah, about a 30% error. So that's more like what we would kind of expect from CFD results, and I'm pretty okay with them results, especially considering we have not looked into the wall effects too much. We haven't put in a friction coefficient or anything, so I'm quite happy with having a drag coefficient of about 30% error here, especially given that the lift coefficient is quite good. So these are, you probably could get more accurate values than the values I've got in here, but again, that would take doing a mesh independent study, doing a domain size study, maybe looking at some more of the wall effects, improving the mesh quality, taking a look at time dependent effects. There's lots and lots of different things we could do here to improve our accuracy, but with improving accuracy takes improved effort, improved computational costs, so there is trade-offs to trying to get your answers as close as you can to experimental data. And not only that, experimental data published such as this is not the end all be all. Some experiments are different than others, there is tolerances involved in error, so we can't take the values here as set in stone also. So you can see that getting values as close as we can and within the range with reasonable values, and getting simulations that follow the same trend as the experiments is more what we're aiming for, rather than getting exact numbers from our CFD, if that makes sense. So the main value in CFD is we'd expect that as we increase the angle of attack, we should get a line similar to this with a similar slope. We should get similar values for our lift and drag, and our simulations should follow similar trends to our experiments, and then we know that we're simulating, our simulations are accurate in the sense that they're representative of the experiments. And then the beauty of CFD is then once we know that our simulations are accurately represented in reality for this case, we should expect to change flow conditions and then still be getting accurate results. So I should be able to change the velocity to 44, 43 down to 40, and for the most part I should be confident in my results that I'm representing reality properly. So but doing an experiment, for example, it might not always be available to change quantities that easily or change the geometry that easily. So this is why we use CFD, and this is why it's valuable. So once the simulation's done, let's take a look at our results. So moving down here to the graphics, we can create a velocity contour and just take a look at how the velocity field is behaving. So I go to velocity contour, just going to give this a name, change this to velocity, and velocity magnitude is fine for now. Just hit save display and it should display the velocity on this symmetry plane here. So you can see what we get is we get our velocity slowing down and reaching a stagnation point at the front of the airfoil, and then we can see the effect of the boundary layer being represented, and we have our no slip condition at the wall. So this looks quite good, and then we get a little bit of separation here at the not really separation, more just the flow, having a discontinuity, let's say, at the trailing edge of the airfoil, and then that affects the flow all the way back to the edge of the domain for the most part. So this looks quite good. Now let's look at the pressure, and this is quite interesting because I'll be able to explain how an airfoil works. So let's go to pressure contour, static pressure is fine, and display. So how an airfoil actually generates lift and how airplanes actually fly is what we get is, you'll see we have at the lower end of the airfoil, we have a region of higher pressure, and above the airfoil we have a region of lower pressure. So what we actually get here when we have low pressure is we have the airfoil's top surface being pushed upwards as it's being sucked by the low pressure. Whereas below here, as you can see, the green contour represents a positive pressure. We should expect to see the force pushing the airfoil up below. So the way an airfoil works is we get a kind of a sucking force upwards and a pushing force below, and that causes a lift force. Now there is regions of negative pressure here, and that's because we have a 0-degree angle of attack. And what you'll notice is as we increase, we'll move now to a different angle of attack, and you'll notice you'll get a much more pronounced effect between a lower pressure region on top of the airfoil and a high pressure region below. That creates a much bigger lift force on the airfoil. So yeah, essentially that's how an airfoil works, and we'll explore that by changing the angle of attack shortly. But one more thing I want to look at before I move on is have a look at the velocity vectors. I'm just going to call this velocity vector and do it by magnitude again. And for the velocity magnitude in this case, I had to change the scale here to 10 before I could see anything, and click fluid surface body. So the velocity magnitude is scaled by its actual magnitude, so we have to play around with the vectors a little bit to get the size we want. So to more accurately visualize this flow, I will change the vectors a little bit more. Let's go in here to vector options and do fixed length and hit apply and see how that changes it. Okay, so now the vectors are too big, so I'll change this scale again back down to 1. Hit save display. Still too big, so let's try 0.1. Yeah, it's starting to get a little bit smaller now, so let's maybe change this to 0.05. So depending on what angle of attack and what airfoil you're running, sometimes the velocity vectors takes a little bit of playing around with before they make any sort of sense in terms of how they look. So I'll actually change this right the way down to 0.01. And now this is much more clear. So you can see the flow comes in and we get sort of a stagnation region. Not really recirculation here, but just stagnation. And then the flow will go over the airfoil. We get zero flow at the wall, of course, due to the no slip condition. And then the flow here just continues on. So I'm happy enough with these results. And now we'll move on to a different angle of attack. So when we change the angle of attack in this simulation, what we need to do is we're going to enforce components on the flow. So for example, given the angle of attack, we're going to change the velocity components, such as the x coordinate to be the velocity times the cosine of the angle that we're going to be simulating. And then for the y velocity of the component, which was originally 0 when we had a 0 degree angle of attack. We'll change that to be the velocity magnitude times the sine of the angle that we're simulating. And also what we need to do is we need to change the lift and drag force vectors, because the lift and the drag is always measured perpendicular and parallel to the relative flow direction. So you'll see the lift is always 90 degrees to the flow direction, and the drag is always parallel to the flow direction. So whereas before, when we were defining the lift and drag coefficients, we left the velocity, we left the force components the same. We're going to actually need to change them now in this simulation when we change the angle of the flow. So if we want to simulate, say, an 8 degree angle of attack on this airfoil, what we do is we go to the velocity section, and where we had an x velocity of 45.6, our x velocity is now going to be 45.6 times the cosine of 8 degrees. So if I go to, on my calculator, 45.6 times cos of 8 degrees, I get 45.156 as the component of velocity, and the y velocity upwards is going to be 45.6 times the sine of 8 degrees. And that gives me 6.346. And if you were to calculate the magnitude of the x velocity squared plus the y velocity squared, this should still equal to the 45.6 that we originally had for a velocity magnitude. So hitting apply, now the flow will be tilted in an 8 degree direction towards the airfoil. And we also need to change the force vectors of the drag and lift coefficients to be parallel with the flow, so, or perpendicular in the case of lift. So if I go to report definitions and go to my drag coefficient, as this is the most simple one to do, we want the drag force vector to be parallel with the flow, and we know we've tilted the flow now 8 degrees, so the force vector that's parallel with the flow is going to be cosine of 8 degrees in the x direction and sine of 8 degrees in the y direction. So cosine of 8 degrees, I'm just going to type it into my calculator, is 0.99, and the sine of 8 degrees is 0.139, and hit OK. And what I'm essentially doing here is just changing the force vectors. Rather than being 1, 0 along this direction, now that we're tilting the flow, we need to tilt the drag force vector with the flow. And just by simple trigonometry, you could work this out yourself using some simple trigonometry. You can work out that this drag force vector here has components cos 30, sine 30, and the lift is going to be in the x component of the flow. It's going to be minus sine of the angle, and in the y component, it's going to be the cosine of the angle. Okay, so minus sine of 8 degrees here in the x direction for that force vector is going to be 0.139, and in the y direction we're going to have a cosine of 8 degrees, and it's going to be 0.99 for the force vector for the lift coefficient. Now if I reinitialize my solution, hit OK, we should get a flow at 8 degrees here, and our lift and drag coefficients should represent the lift and drag for an 8 degree angle of attack. And if we have a look at the simulation data here, or sorry, the experimental data, at an 8 degree angle of attack, we'd expect the airfoil to have, let's scroll along here. So I'm getting about 1.05 by looking at the experimental data here. If this line here is 1.1 for the lift coefficient, somewhere in between here will be 1.05 is what we'd be expecting for our lift coefficient. And for our drag coefficient, if we go along here and go to a section lift coefficient of 1.05 would be somewhere about here. Move our mouse up and go to the circle here. This represents a Reynolds number of 3.1 million. Go across here, we can calculate our expected drag. Expected drag is somewhere about 0.11, 0.115 ish. Somewhere in between 0.011 and 0.012 is what we're expecting for our drag coefficient. So these are expected answers from the simulation. So clicking run here, we should be able to get our answers and compare that to the experimental data. So having a look at the results here, even after about 80 iterations, we can see our lift coefficient is almost exactly what we predicted there of 1.05, which is really good, and to be honest that's probably just by chance. And looking at the drag coefficient, we got about 0.0014. So if there's anything I'm noticing from my simulations here, is that my lift coefficient is pretty good, but my drag coefficient appears to be predicted a bit higher by the simulation. So that's one trend I can notice here by running different angles of attack. So now my solution has converged, and let's take a look at the results. So I'm going to take a look at the pressure contour, and you can see here we're getting the results I described before, where we get a positive pressure below the airfoil that's causing the pushing force upwards of the airfoil, and then we get a low pressure region above the airfoil. This is a negative pressure that's causing the pulling of the airfoil, and this is what's creating the lift, and specifically what creates a higher lift for a higher angle of attack. It's due to this flow phenomenon here. Now we'll take a look at the velocity contour. Hit save display, and you see we get similar velocity profile, but the flow is starting to kind of tilt in this direction here. And it's essentially as you increase the angle of attack, once it gets to a certain point, the airfoil will stall, which is where it reaches its maximum lift coefficient, and then any increase of angle of attack above that point causes recirculation of the flow above the airfoil, and essentially the flow separates and you don't get any increase in lift, and it becomes very unstable. Now let's take a look at the velocity vectors, and I might even make the vector just even smaller again so we can properly visualize this here. So let's make this 0.05. And let's investigate the flow. So as you can see, we get the flow accelerating around the airfoil here, and our boundary layers being accurately represented by the no slip condition here, and I'm happy enough with the results here. So what I will do also is I forgot to show how we check our y plus, our final y plus value for the simulation. So I go to plots, go to XY plot and create new. I'm going to call this y plus versus location. And if I go to turbulence and wall y plus, and it's going to do it in the direction of the vector 10, which is what we want. Do it on the fluid surface body, and then, sorry, we're going to do this on the airfoil, not the fluid surface body. Hit save plot, and we get to see the y plus at all locations. So you can see at the leading edge of the airfoil we get a y plus of about 1, just at the 1.041, which is just above 1, so it's fine, to be honest. And then it decreases along the airfoil, and this is where it's really important. Along the boundary layer here is what's being represented here, and it goes down to about 0.007, so it's below 1 at all locations here for the most part, except for this spike here. So I'm very happy with the wall y plus here. So that was the NACA2412 Airfoil simulated in ANSYS Fluent, with the full geometry tutorial, full meshing tutorial, and the full results tutorial, and we had a look at the effect of changing the angle of attack on the airfoil. So I hope you enjoyed, and leave me a comment below if you'd like any more simulations for me to do. I'm more than happy to take your suggestions into account and do a few. I rather do 2D simulations, to be honest, because this simulation here is, anyone that watches the video is able to conduct a simulation, but I'm happy again to do some more 3D simulations, the same as before. But nonetheless, just leave a comment below of any simulations you'd like to see me do, and I'd be more than happy to do them. And thanks for watching.